Yeah, question 4 here. We're looking for the derivative of the inverse function given f of x equals 4x cubed. So we're going to start there with y equals 4x cubed. Look, I think part A, we actually need to find the inverse function first. Then we're going to look at how to get the same result for the gradient of the tangent using that slightly simpler method that we've got. So just jumping over to Desmos here quickly, we're obviously looking at we can find an inverse of this function over its entire domain. It's monotonic increasing. Yeah, that's just quite easy to see. It's always increasing. It's a one-to-one function already. There's only one x value for each y value. And it passes the horizontal line test. So we're not going to have any issues here finding the inverse function. In fact, we can just quickly plot the inverse function to see what we're going to be dealing with. There we go, that blue line there is going to be our inverse function. So let's double check what that's going to be algebraically over here. So y equals 4x cubed, yep. First step of finding the inverse. I'm going to try and stick to always doing the inverses in green. So the first step, swapping the x's and y's. Now making y the subject, y cubed, x on 4. Y equals cubed root of x on 4, or to make it a little bit simpler to differentiate, x on 4 to the 1/3. So now we are finding the derivative of the inverse. Let me see if I can even keep those going in white, just so we can. So now we're looking at derivative of the inverse. So that's going to be 1/3 x on 4 to the power of -2/3. Really important, remember to always times by the derivative of the brackets. So timesing by the quarter there. So that's going to be 1/12 times x on 4 to the -2/3. So perfect, that's the derivative of the inverse there in the white. So I'll just switch back to blue as the normal colour. What we're now looking for in part B, so this is part A that we've just done there. That's the derivative of the inverse function in terms of x. We're going to jump back over and look at it a separate way, but I'm just going to quickly jump onto B, part 1. It's still asking for the equation, is it? Yeah, it's just asking for the gradient of the tangent. So gradient of the tangent is just subbing in, so we're looking at the point 4, 1. So again, just a lot of the time it helps just to visualize what's happening over here. Was it 4, 1? Yeah, so the point 4, 1 lies on our inverse. So we can see that quite simply here. 4, 1 is there. I'll just plot it so that it's nice and easy for us. Yeah, 4, 1. So we're looking for the gradient of this tangent here. And yeah, it translates from the original curve because the point 1, 4 is on the original curve. So when we swap the x and the y value, or reflected in the line y equals x, which we can just chuck in here as well, we can see that this point is just going to translate straight over to the point 4, 1. Another really important part of inverse functions. So at the point 4, 1, the gradient of our tangent, we're just subbing into here. So subbing in the 4 on 4 to the -2 on 3. This is nice and easy. This is just 1, and 1 to any power is always going to be 1. So the gradient of the tangent is, nice and simply, 1/12. So that's one way of getting to that, by finding the derivative of the inverse in terms of x. It can get quite messy if you've got to do this. So we do learn that sort of shortcut way of finding the derivative of the inverse. So I'll just do that down the side here, and I'll show you that it's going to end up with the same result. So we are looking at the first thing we do if we're starting with the original function is we just start by x equals 4y cubed, that same process. And then again, I'll jump over to white because what I'm going to do is start finding the derivative of the inverse. So the first thing I'm doing within this is dx dy, and that's going to be 12y squared. So now we're using the result that we know that dy dx, because that's what we're actually after, the derivative of the inverse in terms of x is equal to 1 over dx dy. So that we know that the derivative of our inverse in terms of x is going to be 1 over 12y squared. Okay, so now sort of jumping to doing part B for this one. We're at the point 4, 1, but to find the gradient of the tangent here, we're subbing into this one here. We're subbing into this expression. So the gradient of the tangent using dy dx in terms of y, so the gradient of the tangent there is going to be 1 over 12 subbing in the y. So it's just going to equal 1/12 for the gradient of the tangent. So I said two ways of doing the same thing. This way we've actually found the inverse function first in terms of y, differentiated that, subbed in the x value, and it's got us gradient of the tangent being 1/12. And look, this isn't too complicated original function and inverse, so it's not too bad, but you can see it's a little bit extra and a little bit trickier than just doing this method, which is going to be much easier for a majority of these functions and the inverses that we're dealing with. So just then going through, that's the gradient of the tangent. So then part 2, the gradient of the normal, well, it doesn't matter which way we've done it now, we know that the gradient of the tangent times the gradient of the normal equals -1. Therefore, with the gradient of the tangent being 1/12 times the gradient of the normal, so the gradient of our normal is going to be -12. Perfect. So that's question 4. Hopefully that's helped a bit with the understanding of that part of it. Like I said, always really important, I think, to be doing these questions with Desmos open, so that you can be putting in the original function and then also graphing your inverse just to check what's happening and that you're getting it right. Cool. There's that one done, and some more videos to come.